Okay, next we go to part 2. Now we're going to deal with other kinds of measurements, and this is focused now on the management professional as information or measurements that are necessary to do the design and layout of the installation. The particular measurements we're concerned with are mostly intensity measurements, but also spectral measurements may come in handy, but they may not be essential either. We will go through both and talk about how they are obtained. So the goal for part 2 is to understand the needed manufacturing specification of the luminaire during design and layout. For that, you need measurements. Understand how we can take an IES file, which is obtained from goniometric measurements, which we'll discuss lately, and how this file can provide measurement of the power in given bands and the total power that is emitted in the UVC by the luminaire. And finally, how to obtain accurate spectral measurements is also discussed. Although this may be less of an issue since you buy luminaire for a given application, you already sort of assume what spectral measurements are there, but they may be important in addition. So now we're now talking to the management professional. If you're doing the layout and design, hopefully after this training, you will know what an IES file is and how to use the IES file, usually with specific design software to provide all the information you need. And you should be able to specify what type of UV luminaire should be installed, how many are needed, and where they should be placed. This doesn't depend only on measurements, but on the room layout and the requirements of the room. And you will know what is required to obtain good spectral data. I'm aware of 2 software packages, one from Acuity Brands called Visual and Signify called Relux, which are layout packages or software that can take input of an IES file and use it to help design a room and to know how much radiation is in any given part. So the software then provides schematic pictures of the intensity distribution in a given space. And the IES file also gives you zonal power. That is, the lab will provide the zonal power. Some of this may be available in Visual and Relux as well. And from the sum of the zonal power, you get the total radiated power of the luminaire, depending on its configuration, either over 90 or 180 degrees. Now, an IES file, how do you get it? Well, the manufacturer should provide it. That means he has had his device measured goniometrically, and it is a file that contains the radiant intensity data at various angles of a given luminaire goniometer. And we're going to explain how this works in some detail. The intensity distribution of the IES file usually should be traceable to an accredited laboratory. In other words, if the manufacturer provides it, he should be able to say who made the measurements and whether that laboratory is accredited. If it's not accredited, then you may question its accuracy. Again, we're going to go through the fundamental quantities we did before. notice that we are now focused on going to the right, the radiant intensity. That's what we're interested in. Before, in the first part, we dealt with radiant irradiance. And so we're now going to deal with angular measurements rather than aerial measurements. To get angular measurements, we need a device that will either rotate the fixture, but hopefully the detector around the luminaire in such a way that it provides a map, angular map of all of the radiant intensity of the luminaire. So this is looking at a type C goniometer. In the visible region, we often use a mirror photometry, but mirrors don't work very well in UVC. Glass does not transmit or reflect. So we basically have a UVC detector mounted at a given, on another arm, given distance away. And notice that the arm rotates around the luminaire. It goes 360 degrees around the luminaire normally. And on the other hand, the device itself can also be rotated and set at various angles, so that we get, when we are done, we're going to get a map of angular distributions on a sphere with two sets of angles. One is called the mirror or the vertical angle, and the other is the lateral angle. Okay, I guess I got ahead of myself a little bit. The vertical angle normally takes data every 1 degree, 2.5 degrees. It can even go lower than 1 degree if needed. The lateral angle, that is the rotation of the luminaire itself in a horizontal plane. Usually, depending on how focused the beam is and the application, 22.5 degrees is typical, but if needed, it can go down to 10 or 5 degrees. Obviously, the more angles you have, the longer the measurements take. Goniometric measurements of a luminaire normally take on the order of half an hour to an hour to complete, so it is not a quick measurement. The output of the software that comes with that goniometer is an IES file, and I give you a picture of a part of a IES file here. It has headings, as you see here. LM63 is the document that describes how IES files are generated, who the test lab is, who the person who wanted it is or is paying for it, and so forth and so on. This is filled out. The electrical issues are put in, and then over I highlighted in the second column that says excimer sample, no filter. So this is the 222 nanometer lamp where the filter, which is normally on there, has been removed. And then below it, you begin to see a whole bunch of numbers. And so the first, ignoring the first, I want to look at the block of numbers that starts at 0, 0.5, 1, 1.5. So this is the vertical or mirror measurements, or the detector rotation every half a degree. So we will have data every half a degree from 0 degrees to 180. So this is the first block of data. And then the second set of data is 0, 22.5, 45, 67.5, 90. These are the lateral angles. So we will collect data at those 5 lateral angles, and basically 360 measurements at each one of those. Now below it, you begin to see the data. 147.7 is the measurement at 0 degrees on both vertical and lateral. And the 147, this is all at 0 degrees lateral. So we get 150 measurements. And notice, however, that the measurements are maximum at 0 degrees, in other words, normal to it, and then fall off with angle and reach 0 before 90 degrees. And above 90 degrees, since it is pointing down and all the radiation is in one direction, we expect it to be 0 above 90 degrees. So this is the way an IES file looks. There are multiple pages of this. You obviously have data then for every lateral angle. And software can collect this and make very interesting pictures from it. One of the things that the plot is the plot of the radiant intensity and visual representation. So we notice that at the center at 0 degrees, this is on the mirror angle. We have the maximum value, and the value is you see here that every 45, 60, 75. This is the intensity values. So we have an intensity value somewhere around 115, and then, but as we go along with angle, we find that it falls off rather rapidly. And by the time we get to 30 degrees in both directions, 30 degrees, we are down to less than half of the amount. And there are slight differences. The two plots are one done at 0 degrees lateral angle, and the other done at 90 degrees. So the device is not quite symmetric, but it isn't very far from it either. So this is of the device. We can do another one, and we put a diffuser on top of it. The diffuser tries to make the light spread evenly. And now we notice that we've reduced the center light significantly by a factor of about 5, but we have thrown light at more angles. So now at 30 degrees, we have about 3/4 of the light remaining, and light comes out all the way down to about 75 degrees. We can get light out. So we've almost made this into a circle. If it was a circle exactly, then it would be what's called a cosine distribution. In other words, even radians. So these are visual representations from the IES files just by plotting them in this way. Another thing that is provided by the software is now called the zonal radiant power. I'll explain how this works, but you notice on the left-hand column that you have zones of 10-degree strips in the vertical direction, and the amount of radiant power in each one. And then you sum that up to get 102.2 milliwatts is the total output of the device. And then 10.9 over 102 is 10%. So notice that while the peak intensity is at 0 degrees, the radiant power maximum is at between 20 and 30 degrees. But then again, it falls off rather rapidly. Above 90, the second middle column, you see there's no light at all. And then the third set on the right basically it takes the zones and makes various configurations. That is the software can do that. Okay, I want to show how the zonal power is done. And we want to calculate between 10 and 20 degrees. So first is we obtain the average intensity from the reading between 10 and 20 degrees. And by averaging the mirror at all the intensity, we get 109 milliwatts per steradian. Well, and then there's a zonal factor, which in the next two things here, the zonal factor is 2 pi times the cosine of the 10 degrees, and which is 0.1745. So the zonal factor Z10 is 0.0955. But Z20, the zonal factor is 3789. This is, and so forth. So if we want then the difference, the zonal power, we multiply the average intensity times the zonal factors. One subtract 10 from 20, and we get 31 millivolts. So 0.37 times 109 minus the 0.09 gives you the 31 millivolts. And throwing back, we see here that at 10 to 20 zone, we had 31 milliwatts. So this is how the calculation is done, as a repeat. Okay, so now we have the total power of the device, which is going to be very useful. In the case above, we had the amount of total radiated power. We can divide that power by the volume of, say, an upper room, and this is the volume above 2.1 meters. So it's the volume of the room minus the volume below 2.1 meters. And so this we call the power density. It's obviously the watts per meters cubed. And that's the best measurement units to use. It could be milliwatts per meter cubed as well. If we know the microorganism's volumetric inactivation rate, then from the PV value and the size of the room, we can easily get how many luminaires we need to get reach that inactivation rate, or some multiple of the inactivation rate, depending on what the focus of the design is. However, usually volumetric information is not known. Rather, what is known often is the average irradiance that's necessary. Here's a way of obtaining the average irradiance. From the data we had before on the previous slide, we had the volumetric power, the watts per cubic meter. If I now multiply that by the path length, which is in the figure kind of given as R, it's the average value of the radiation, which typically is the distance to the wall, but note that R changes as I move it along the wall horizontally, and as I hit the side wall, it changes, it becomes shorter. As I go toward the corner, it gets longer. So we need to average that, and that's not so easy. But if we now know the microism fluence inactivation rate, which is often what is published in publications, then the number of luminaires needed can be estimated. By the way, this way of doing it with an average ray was done by Luckish and is published in his 1946 book. So it's been in practice for upper room radiation for 80 years, and probably before that. Okay, shifting to spectral measurements. In the UV, spectral measurements are done using a double monochromator, and it's done in the dark room, obviously. And usually the instruments that are obtained, the scanning instruments, scan over the UV and the visible region. I show an example here from 200 to 800 of a low pressure mercury lamp with the 254 radiation dominating, but you see that there are small blips of light. And this, by the way, is a picture from the lamp presentation. And you can mount the detector or the source, depending on how you want to do it, on a rail. And so you can set a fixed distance between the detector and the source and measure the spectral output. And from that, the collected spectral output is obviously the power, the radiation. If you sum over the spectral irradiance over the nanometers in the UV, then you get watts. In this case, watts per meter squared, or watts for whatever units you're using. You can also mount the source on the rail on a mounting device that can rotate in two angular directions, orthogonal directions. So you can rotate it up and down and rotate it horizontally. This way you can obtain spectral data at an angle if that is important. For low pressure mercury and LEDs, it usually is not important. The spectra does not change, but for excimer sources, it does, and so it becomes important in that case. Some caution: spectral measurements is difficult. First, the sensitivity of devices in the UVC is not as good as visible or UVA. And on top of that, the signals are much smaller usually. So to get accurate spectral measurements, we need to look at very small signals. And that's why you need double monochrometers, because normally the source has other light, particularly if they're incandescent in the UVB and visible that far, and it is orders of magnitude more than in the UV. And furthermore, calibration of the signal that is more difficult. And sources used for calibration have much lower levels of a signal, and we have to filter out the unwanted radiation, just like we did for the standalone detectors. So that means a double monochrometer is required. Many companies sell these that are good from 200 to 800 and even further, depending on how much you want to get in the device. But even for the relatively cheap ones, they are expensive, and usually certainly an installer will not have these. It requires a lab to have these devices. And to calibrate it, you need two sources. That's because you would want to use a deuterium gas, which will calibrate over the UVC region. But the deuterium lamp output is not stable. And while the spectral data, it's stable, the intensity is not. So when you make the spectral data, you then also measure a tungsten quartz halogen lamp, usually 1,000 watt, 500 watt lamp, which has been calibrated all the way to usually to 250 nanometers and up. Then you find a region in the UVB around 300 nanometers where you can have enough signal from both that you can then normalize the deuterium lamp signal to that of the quartz halogen and stabilizes the deuterium lamp output. Standard lamps need to be purchased from NIST or another accredited laboratory that sells these things. There are not many in the United States. And if you use simpler detectors, you have to somehow get them calibrated against a standard. And that calibration should be done regularly, and filters to block out UVB and visible need to be verified as to what effect they have in the UVC. Okay, so we're done. Summary then is when you want to do an installation and want to do a layout and installation and want to calculate how many units and where to place them. The units need to be effective, that is, to reach the inactivation level that is wanted. They also have to be safe. So the IS file is used for the UVC intensity, and with the digital design tools can then be used for layout to find what the total wattage in the area of irradiation, what the concern is. And so from the IAS file, the important information is that the total irradiated watts needs to be at a level where the inactivation of the microoccurrence of interest happens at a rate that is acceptable. Spectral information, not a whole lot to say. Again, a spectra should be provided by the manufacturer. If there is spectra that you would want to obtain that is not available from the manufacturer, then you need to go to an accredited laboratory. And for krypton fluoride excimer lamps, depending on the type of lamps, measurements at various angles becomes important because the spectrum changes significantly with angle. Thank you.